Hello, I'm Joseph,
My name's Kevin.
I'm Jeesrael.
And I'm Lensar.
and our project was a pull-down closet hanger. We are in the class of ME154, Mechanical Engineering Design, from San Jose State University.
For our project, the problem we sought to address was that the closet rods are simply too high to reach for certain individuals. Standard closet rods are mounted to be around 66 to 72 inches above the floor, which can be too high for which which is too high to for some individuals like shorter children and those with mobility issues. We found that 48 inches was comfortable enough for majority of people with said issues, and thus need to bring the closet rod down to 24 inches. Other issues we saw to solve was the cluttered closed waste usable space. Typically, there's more vertical space that could be used if there was a lowering system to bring the bars within reach. The working principle behind our mechanism is a four-bar mechanism. A fixed mount attached to the opposing side walls within closet acts as a ground link for the four-bar. Then the two coupler links acts as a guide to the arc the hanger arm into its actuated lower position. To manipulate the forward mechanism, the user would pull down the pull rod attached to the closet bar itself. Being attached to the closet bar gives the most control over the speed and strength needed to actuate the mechanism.
And so for our first design that we came up with, it was a simple four-bar mechanism with the tertiary link extending past the four-bar and connected to a closet rod. And this gave us a kickstarting toward design process of how we wanted the movement to be. But there came some problems with the first design, mostly being we couldn't find a way to actuate it consistently, as well as the yellow link and the green link. They created a toggle position which would lock up when the user is actuating. And then also, when stowed away in its upright position, the entire mechanism sat further off of the bracket, further forward from the bracket than we preferred to. So we wanted to make it more compact. So we settled upon our final design. Design 2 was loosely based off modified cabinet hinge. And then things we changed from this motion gen versus our final prototype was that the handle was omitted due to it creating some external torsions we didn't account for. And we used a pull string to actuate the bar instead, as well as we moved the spring location higher up to give a more consistent spring tension throughout the pull. This is our CAD design that we came up with. This is just the isometric views. As you see, the bar sits between, and then these brackets on the sides were mounted on opposing walls. This is the side view for more clarity. And this is our prototype in action. And this is the stow position with the closet bar being upright, and it's much more compact compared to our design one. And then this is our applied load position where the bar is lowered.
When it came to the force analysis, we couldn't really fully utilize the tool we were given, and because of the issues we came across, so this was the values we were able to input.
All right, the first stress we looked at was that shear stress, which mainly affects the pivot points. These pins support the rotating joints, so they experience force across their cross-sectional area. In early testing, the 3D PLA pins failed in shear, so we had to replace them with steel punch pins for higher strength. Next is bending stress, which occurs at the coupler links. These links carry the load from the close and guide the hanger through its motion. Since repeated loading caused some bending in the PLA links, this showed us that stronger materials would improve the final design. We also consider tensile stress in the pulling string. The string is loaded in tension when the user pulls down to actuate the mechanism. We replaced the original wooden lever with a high-strength string because it lowered the force needed and made the system easier to use. Finally, the last stress is bearing stress, which occurs at the mounting bracket. Where the load is transferred into the wall, the bracket also helps spread out the force so that the mechanism stays secure and reduces the chance of pullout. For safety precautions, we made 3 main improvements. We added retaining rings on the dowels to prevent the bar from slipping, replaced the weak printed pins with metal pins, and used a high-strength actuation string to make the operation smoother and safer.
So for failures and problems that we encountered during fabrication, we encountered that the 3D printed pins broke during actuation, as we previously mentioned. The root cause of that is that the PLA shear strength is insufficient for pin loading. The pin diameter and the cross section was too small. So then our fix would be to replace it with steel punch pins, which gave us higher shear strength. Also, the copper links began to bend. This is because of the repeated cyclic loading caused by the bending in PLA links. We could look into stronger materials like PETG that have higher strength. We also experienced excessive dead space in the links. This is due to the added spring and string that caused the links to be pulled, deformed, and creating an angle in it. The fix for that is that we could update the design, like the shortening out the dowels. And then lastly, the handle was not included in the prototype. This is because this omitted an uneven force balancing and twisting. And then our fix would be to have a pull string that's substituted for the actuation in prototype. So the choice of materials, we chose high strength PLA, because it provided us a rapid prototyping. So if we needed to change parts, we could do it, or change the design, we could do it. It's also cheap. However, it is weak under high extensive load and poor shear strength resistance. Another material we had was wood. It is a abundant resource. It's cheap and easy to fabricate. However, due to the loads we were going through, it splintered easily. So concluding this project, we have demonstrated our project scope, the analysis, how the hanger works, and then the things that we can improve on. Thank you.